permutation is an arrangement of objects I forgot the word of, arrangement of objects where the order matters. An arrangement of objects where the order matters. We're going to spend about 3 to 4 classes on permutations, 1 on combinations, 1 on the binomial theorem, so this permutation is going to take us longer. It wouldn't be in class time anyway, so we'll talk after. Okay. An example is license plates. So my license plate is BAT950. It's the Batmobile.
Mine's GTA. How cool is that?
My boyfriend's is F me. Let's say I don't care about the order and I just rearrange these. So I'm going to say TAB509. Does that matter? Is that the same license plate? That's a permutation. So if you flip the order of something, it's not the same. Example, phone number. Right? If you're texting your friend and you just put the 7 numbers in any order, does it matter? Absolutely. Postal codes are permutations. Anyone want to guess what the definition of a combination is? Let's focus on math class. Now you're going to find out society has lied to you for the past 18, 17 years. Who opened their locker this morning? What did you use to open your locker? Did you? Is it a combination? So if you just take those 3 numbers, any order you want, is the locker going to open? Nope, it's a permutation. It's a permutation. We have lied to you. So what's an example? Hands of cards. Let's say we're playing poker and I have the hand that has 3 kings and 2 tens. Any poker players can tell me what hand that is? Flush. 3 of a kind and a pair makes a full house. So that's a pretty good poker hand. Well, what if I just wanted to arrange it differently in my... What did he say? What did he say? What if I just wanted to arrange it differently in my hand? Let's say I wanted a king and then a 10 and then a king and then a 10 and then the king. I want to alternate the cards. Why? Because I like that. Does that change my poker hand? No. What if I put the 10s first and then the kings? What if I put 2 kings and 2 10s and then a king? It's still the exact same poker hand. That's a combination. Okay? Key is that order matters for permutation. So yes, we have lied to you about your locker combination. What about a McDonald's combo? Does it matter the order they put it on the tray? If they put burger, fries, drink, or drink, burger, fries, does it matter? Is it still the same combination? That one we did not lie to you. We would not mess with McDonald's. That is a combination. So we're going to spend, like I said, about 3 or 4 classes on permutations. Combinations don't need as much. Read to read example number 1. I'm just going to pause for a second. We've done this whole read to understand thing all semester. And the reason I want you to do that is, number 1, the read to read calms your body down. So I know you've all been in that situation on a test, a quiz, an exam, where you start to read the word problem and you're like, oh my God, this is a lot of words I already don't understand. I don't know what's going on. By the time you get to the end, you're stressed. Well, reading it the first time is going to calm you down because now you're going to go back and reread it. What the read to understand does is make sure your brain doesn't skip any words. Because what happens when you just read something once is your brain gets the beginning and it's already reading the end of the sentence and it's skipping over important words. So even if you haven't practiced it all semester, it's a really good idea on the exam to read, then take a breath, calm yourself down, then you read to understand. If you're not a highlighter circler, that's fine, but at least then you're slowing your brain down. So read to read, the new Bomber Stadium has 5 gates, and how many ways can you enter and then leave the stadium by a different gate? This should be then, not than. I be not your English teacher. Yes, he has sent me many nasty emails about my typos. Now we read to understand. What is important? Do we really care it's the Bomber Stadium? No. Do we care it's a stadium? No. What do we care about in the first sentence? 5 gates is all we care about. I don't really care, in essence, what kind of building this is. What do we care in the second part? Well, what's the question piece? Okay, enter, then leave. Different gates. Okay. Really good idea on the exam to read it to read, calm yourself down, then read to pick out the key information. To answer these kinds of questions, we use this sounds so important, fundamental counting principle. The fundamental counting principle, which we call the FCP for short because words scare us. The fundamental counting principle says if one task can be performed in A ways, A being a variable, not the word a, and a second task can be performed in B ways, then the 2 tasks can be performed in A times B ways. Grab your paper and I'll repeat all that in English. So earlier when I said get out your paper and be all ready, clearly you were listening to that. Yes, I was here. They fired you?
Fired, not fired.
Post-seasonal cutbacks?
No, the district manager came in and just shut the store down. Everybody lost their jobs.
Like every source or just your one store?
Our store, like everybody working at the store just kind of was done. No, it wasn't even that dead. We looked really
But you were my battery hookup person. I don't know what to do with this. That threw me off my game a little bit. Okay, fundamental counting principle. First thing is we use blanks. Blanks represent the number of choices. So for this question, I'm going to draw 2 blanks. The first blank represents the number of ways to enter the stadium. The second blank represents ways to leave or ways to exit. How many ways are there to enter the stadium? So you have your Bomber ticket, you walk up to the stadium, how many different ways can you go in? But how many ways can you leave?
4.
Why 4? And the fundamental counting principle says we multiply. There are 20 different ways to enter and leave by different gates. That's about as much work as each question is going to take. Okay, these aren't big identity or log questions that are going to take a half page. That's usually it. This is showing your work. Question number 2, read to read. Take a deep breath. Read to understand. What do we need to know?
3 digits, ways, numbers.
Yeah, I like numbers. What's a digit versus a number?
3 digits is like 100.
Kate, what's the difference between a digit and a number?
A number has a value.
Number has a value. Numbers can be more than.
Numbers are infinite.
This is a fun game. I enjoy this. So a digit is one number. A number can be made up of multiple digits. So how many digits are there in the world? Well, let's count. 1,
2, 3, 4, 5,
0. There are 10 digits. If you didn't know that, write that down. There's 10 digits, 0 through 9. What? Okay. There are 10 digits, 0 through 9. Digits make up numbers. Okay. I'm going to put 3 blanks representing the 3 digits in the number. Let's talk about the first number, because it's the little tricky one here. If it starts with a 0, let's say, for example, 021, is that a 3-digit number? No. So 017 is considered a 2-digit number. So I'm going to put the notation cannot be a 0. Okay? You can write that in words if you like better. You could put 1 through 9 to show those are the choices. I just like to put a 0 with an X. That's my notation for can't be 0. So how many choices for the first digit? 9. What about the second digit? Does it matter what digit it is? So how many choices? 9. Okay, now why is it 10? Well, the 0 can go back in, and can we repeat? Could we have the number 333, 444, 666? Okay? It doesn't say different digits, it says different numbers. Okay? What about the last digit? 10. Fundamental counting principle says we multiply. It's the second example. Now, we could have listed them all out. That would have been a fun game. So we could have put 001 and 002, and then we could have got to the 111 and 112. Well, how much time is it going to take to list out all the 300 or the 900 3-digit numbers? That's why we have the fundamental counting principle. It's just a fast way to know the number without having to list them all out and probably miss one. Questions so far? It's only the second example. We're going to go on to the trickier ones, which are called restrictions or permutations with restrictions. I have not turned the page yet. I'm still highlighting. A restriction is a condition that limits the total number of possibilities. Examples: must start with, must end with, must sit together, must not be together. I'm going to talk to the ladies for a second. Ladies, the most painful event in your life, besides childbirth, not that I've done it, but I've seen it, it's not nice, is planning your wedding. Now, what's going to happen when you plan your wedding is so-and-so has to sit with so-and-so, but they don't want to sit with so-and-so because they hate them, and then your side's going to hate his side, and then Aunt Mary can't sit next to Uncle Frank because he gets drunk. It's just not a good scene. It is the most stressful time in your life, is planning that seating plan for the wedding. That's what we're going to practice next is, well, what about people who have to sit together, and what about people that don't want to sit together, and what about numbers that have to stay together, and vowels have to be together, and the consonants can't be by a vowel. So I was talking to the ladies. No, boys, you just show up. Put on a tux and show up. That's it. No, you don't need that. We need to know this. Example number 3. Imagine there's 5 people, 2 of who are Jack and Jill, and they're going to sit in the following arrangements. We're going to put them on 5 seats, then on 3 seats, then on 6 seats, then on 5 seats, but Jack has to be in the first seat. Then Jack's a pain in the ass and he needs to be in the middle. Then he's like, oh no, I need to be on the end. Well, then Jack and Jill get together, so they want to sit together, and then they break up. They're like, no, we're not sitting next to each other at all. This could be people, it could be books on a shelf that need to stay together or can't be together, or you want them from smallest to largest, or you want them alphabetically. This can be arrangements of letters to make words. This can be arrangements of digits to make numbers. They're all going to work on the same principle. 3A is a straight-up standard non-restriction kind of permutation. 5 people, 5 seats. How many blanks do I need to write? 5 people, 5 seats. I need 5 blanks. Just hang on. So this could be any row in this room. Let's pretend it's the middle row. So room is completely empty. Jenna walks in. No one is in her row. Well, she hobbles in right now, but no one is in her row. So how many different choices does she have for a desk? 5. She can pick any desk she wants. She picks the back one and she sits down. Well, then Brian comes in and he has how many choices of seats? Well, he can't sit in the back desk because he'd be sitting on Jenna. That would be weird. How many desks does he have to choose from? So he picks one and he sits down. Then Derek comes in and how many choices does he have? And then? And then? Fundamental counting principle says we multiply. This you would be expected to do without a calculator. So go with whatever your brain sees first. Some brain sees the 5 times 2 to make 10. Some brain see the 4 times 3. Go with whatever your brain sees first. You don't need to always multiply. Why are you talking? And I'm still talking. And why are you all talking? You don't need to multiply numbers in order. So if your brain sees this first, do it first. What's 5 times 2? And then your brain might see the 4 times 3, which is. And then your brain should be able to do 1 times 12 and then add the 0 to get the final answer of 120. Five people, 1 row of 5 desks. There are 120 different ways I can arrange those people. How many desks in this room? Okay, instead of counting them all, how many rows are there? And how many desks are in each row? Because I like symmetry, so I always try to have an even amount in every row. So how many desks is that? 30. How many people are in this room excluding me? Might be easier to count the empty desks, just saying.
22. Oh, 23 including the...
Miss Vila, she counts. She's in a desk.
23.
23. Someone remember that because we're going to come back to that tomorrow. 23 people, 30 desks. Then you're going to be like, in a second, how hard it is to make a seating plan as a teacher. Okay, let's mix it up. What we're going to do now is take away 2 of the desks. So there's only 3 seats. There's still 5 people. It's implied 2 people are going to end up standing. We're not shoving 2 people into 1 desk. That's just weird. 2 people are going to end up standing. 5 people, 3 desks. First person walks in. How many choices do they have? First person walks in. How many desks are there? 3. So how many choices do they have? And they pick a desk and they sit down. Person number 2 walks in. They have 2 choices. They pick a desk and they sit down. Person number 3. Person number 4. Oh, but this represents desks. So what happens when we multiply? Does that make sense? 3 desks, 5 people, that there could be 0 ways. When you have 2 different numbers of objects, so 5 people, 3 desks, the blank should be the lower number. When you have 5 people, 3 desks, the number of blanks should always be the smaller number. Otherwise, you're going to run into the 0 situation. So instead of 5 blanks, we're going to use 3 blanks because 3 is smaller than 5. Now, we don't want to think in terms of desk-picking people because that doesn't really make sense. So we think of this in terms of the first desk. How many possible people could sit there? 5. Somebody does. We don't know who. We don't care. It's irrelevant. The next desk, how many people could sit there? The third desk, where are the other 2? Standing, and we don't care about them.
60.
Offer of 60? So up here, going back to A, this represented the first person, the second person, all the way down to the 5th person. Because that didn't work here, because we're going to end up with that 0, 0, we switched it, used the lower number of blanks. This represented the first desk, or seat, or whatever, all the way down to the 3rd desk. You're going to know if you've picked the wrong number of blanks because you'll run into the 0 problem. So this is interesting. Desks went from 5 to 3, and the number of permutations was cut in half. But the desks isn't in half. Interesting. We'll come back to that. 6 seats. 5 people, 6 seats. How many blanks? 5 people, 6 seats, which was the lower number. Okay, lower number is people, so this has to be the first person, all the way down to the last person. First person walks in, how many choices do they have? They pick a seat and sit down. Second person. Third person. Fourth person. The last person. And what do we assume? One desk is empty, and that's fine. There's empty desks here. That happens in seating plans. Okay, go ahead and whatever your brain sees first, multiply those first. Offer of 120. Ooh, 720. Let's just double check. My brain sees this first. Then it likes the 3 because it's smaller. Then it likes the 6 because 6 times 6 is easy. Then the 2's left over. 720. Okay? That's the highest the exam would want you to do without a calculator. Any bigger numbers, they're going to let you use the calc. Questions so far? Okay, let's get to Jack. Oh, Jack. Jack must be in the first seat. We're assuming still 5 people, 5 desks. Jack has to be in the front. Bad eyesight, can't see the board, so this has to be Jack. That's showing my work. That's showing I understand there's something special about the first desk. You can write it out in words. A J will tell the marker you know what you're talking about. So how many choices for the first desk? Well, it has to be Jack, because he has to be in the first spot. Does it matter who's behind him? Okay, so choices. Agreed? So no restrictions back in A was 120. Just because one person needs a particular spot, we're down to 24. Now Jack must be in the middle. Well, wouldn't it be the same? What do you mean? Why would it be the same? Okay, so we're going to fill his seat first. 1. Does it matter who's in the front? Who's next to him? Who's on the other side? Who's in the last desk? So isn't it the same? Yup. Again, this doesn't have to be people. This could be a particular object that needs to be in the middle of a group of 5 objects. It could be a word that a T has to be in the middle. It could be a number where the middle number has to be 7. Okay, same idea, you're just switching up the number of objects. Oh, Jack, really? What does the end mean? Well, it means the last seat if the rows are vertical, like we are right now. What if you were sitting in a line? So you were sitting in a horizontal row. So imagine you're at a concert, you're at the football game, and you are beside people. What is the end? Yeah, it could be the right or could be the left. So we're going to have 2 separate cases. The first case, Jack's going to be on the left. And the second case, Jack's going to be on the right. And that's because the question just says on the end. It doesn't specify what end. It doesn't say the last seat or the first seat. It's just the end. Maybe he's got a little bladder, has to pee a lot at the football game, drinking lots of beer, needs out quickly. Okay, so let's look at case number 1. What do you notice? Yeah, we've already done this in which question? This is the same as D. So 1 for Jack. Do we care who's beside him? Yes. Sorry. This is it. That's showing your work. Okay, what about the second case? Same thing. 1 for Jack here. First seat, don't care. Second seat, don't care. Don't care, don't care. 24. What do we do with these 2 numbers? Why add them? Why not? Why don't we divide them? Carry my red pen. There are 2 really important words in mathematics. The first is and, the other is or. And is really what the fundamental counting principle is explaining, and what it's saying is that we multiply because we need Jack and a second person, and a third person, and a fourth person, and a fifth person. So and always means multiply. What does or mean? It means add. So case 1 or case 2 means we are going to add these together. Okay, this will help you figure out some of the more complicated questions if you stop and say, okay, is it and or is it or? That will tell you if you're multiplying or you're adding. So how many total permutations if Jack must be on the end? 48. Jack and Jill must be together. Case number 1. They can be in the first 2 seats. I'm just going to circle them. Does it matter whether Jack is first or Jill is first?
No.
So this could be Jack or Jill, which means the other seat is the other one. That would be a little confusing, so maybe JA, JI. So 2 choices for the first seat, 1 for the second seat. What about who's next to them? Do we care? Okay, how many people are left? 3, and then 2, and then 1. Offer of 12? Well, what if they're not in the first and second seat? What's the second case? Second and third seats. Does it matter who's in the second? Okay, so 2 choices. What about the third? Has to be 1, so whoever's not in the second seat. What about the very first seat? So don't care any of the other people. The fourth seat, and then 1. Offer again of 12? Well, what if they're not in the second and third seat? What's the third case? Okay, so we'll fill in the bubble first. Third seat, and then 1. First desk. Oh, but wait, there's a fourth case. Oh, love seating plans, love it. What's the fourth case? So inside the bubble, we're going to get a 2, 1. First 3 seats, don't care, 3, 2, 1.
Do you do this during seat lines?
Sometimes, just for fun. What do we do with the different cases? Well, they're either in the first and second, or the second, third, or the third, fourth, or the fourth, fifth. So we're going to take these numbers and add them, which gives us 48. Well, that's the long way. Let me show you how to do the short way when people need to be together. I'm going to start the same way, 5 blanks. I'm going to circle the first 2. Within that, it's still going to be 2, 1, whoever's in the first, Jack or Jill, and then the other person beside them. And what I'm going to do is just count them like 1 seat. So I'm going to imagine like they're 1 person stuck together. So imagine they're not there and there are 4 desks or 4 people left. This gives us 4 times 3 times 2 times 1. Okay, let's double check. 2 times 1 times 3. Not a trick question. Times 2 times 1 times 4, 48. So this represents the number of objects or people that need to be together. And this up here is the remaining objects plus 1. And all that plus 1 is doing is taking those 4 cases and just smushing it down into 1. If your brain likes the long way, do it the long way. If your brain gets the short way, do it the short way. The problem of doing it the long way is what if there's 10 people? Right? What if there's 20 people? So sometimes it's going to be easier to learn the short way, but it's completely up to you. So this is always the number of objects that need to be together. This is the remaining always plus 1. Well, now they refuse to sit together. At this point, you're like, just go home. the remaining objects plus 1. Follow the logic here. There's either two possibilities in this room. You're either sitting beside Mrs. Vila or you're not. Are there any other possibilities? You're either beside her or you're not. So if we can find the number of ways that two people are together, how can we find the amount of ways that they're not together? If we took all the ways when anyone sits anywhere, we don't care, and we subtracted when they are together, it has to equal when they're not together. So the way we do people who don't want to be together, or books that can't be together, or whatever, is we calculate the total, which I'll explain in a second. We minus when they are together, and that has to be when they're not together. Only two possibilities. The total means anyone sits anywhere, no restrictions, no one has to be first, last, together. So there were 5 people, 5 blanks. This is what we did in part A. And how many permutations did we say in part A? I heard a very weak 120. Then we just did when they are together. I'm going to do the short way. 2 people need to be together. We count them as a group. There's 3 remaining, which means we start with a 4, 3, 2, 1. Again, all that 4 does is does all the 4 cases into 1. We just said this was 48. So how many ways if they're not together? 72. Offer of 72. That's how you do people or things or objects or numbers or letters that cannot be together. But that was all the different possibilities. Okay, let's look at some pins. What does PIN stand for? What does the acronym PIN stand for? Interesting. You probably all have one, but don't know what it means. Personal identification number. So who says PIN number? Because I know people do. That drives me crazy.
That's like RIP and peace.
I know. PIN number, you're saying personal identification number. So you need to create a 3-digit PIN number for your bank card. PIN for your bank card, and you can only use the digits 1, 2, 3, 4, 5. I personally would not bank here. That doesn't seem very secure, but let's figure it out. Part A is what we would call the total. It's just straight up, no restriction, anything you want, except it needs to be 3 digits and those numbers. How many blanks? Why 3? Because it's the lower number. We have 3 digits, 5 to choose from, 3 is the lower number. Choices for the first digit. Now that doesn't represent picking the number 5. It represents 5 choices. How many choices for the second number? So is it 5 or is it 4? Can we repeat or not repeat? Could we have a pin that's 555? Could we have a pin that's 331? How many choices for the last? Again, that doesn't represent your pin is 555. It represents the number of choices that you have. Fundamental counting principle says we multiply because we need a first digit and a second digit and a third digit means? Yeah, I wouldn't be banking here. That would not be hard to crack. How many start with a 3? Okay, so here we're adding a restriction. This is the exact same question as Jack has to be first. We have 1 possibility for the first digit. It has to be a 3. Does it matter what comes next? Just like it didn't matter who sat after Jack, we have 5 possibilities and 5 possibilities. How many of these pins start with a 3? 25. How many are even? So what determines if a number is even? How can you look at a number and know if it's a digit? It's the last digit, so this one is the one that matters. And for this situation, between 1, 2, 3, 4, and 5, what are our choices to make this even? 2 and 4. So 2 choices for the last one. Again, that doesn't mean you pick the number 2. It means there's 2 choices. First digit, does it matter? Nope. The second digit? So are you better off picking an even pin for this situation or odd? Which is more secure? Yeah, how do we know odd's more options? Well, if the total is 125 and we just calculated odd is 50, how many have to be even? 75, right? Because it's either odd or even. How many use only odd numbers? How many use only odd numbers? What does that mean? So it's not asking how many pins are odd, it's asking how many use only odd numbers. What's the difference in those questions? You can only pick odd numbers. So this one has to be odd, this has to be odd, and this has to be odd. I'm going to repeat that. It's not asking how many pins are odd, it's how many use only odd numbers. So what's our choices for odd numbers? And then? And then? Do you see the subtle difference in the questions? And that's what's going to get you with permutations. It's not slowing down and reading the questions carefully enough. And again, you can have one of these numbers wrong and it blows your answer and you're going to be like, what the heck? Okay, so don't get frustrated at the beginning. These are going to get easier as we go along. Okay, let's do some Uber restrictions. Read to read. Didn't we find already their blood pressure's going up a little bit? Using only the digits, this is a lot of stuff. That's what read to read does, is just going to calm you down at the end because you have a second chance to go through it. So what's important here?
Restrictions not allowed, or repetition not allowed.
Okay, so only,
Repetition not allowed.
repetition not allowed. Okay, so the last example we were allowed because the question didn't specify. This we're telling we're not. Part A.
4 digit greater than 6,500.
Okay, so we're going to do a little bit of logic for A. And I'm just going to go through the numbers one by one, and you tell me if we can start with that number. Can we start with 2? Ooh, I heard yes and no, so fight it out.
It can't be, it has to be greater than.
Can't start with a 2 because it has to be greater than 6,500. Can we start with a 3?
No.
Can we start with a 5? Could we start with a 6? Okay, so let's do case number 1 is starting with a 6. What about the second number? Can it be 2? So I heard yes and no. Because it has to be greater than 6,500. Could it be the 3? Could it be the 5? Could it be the 6? Ooh, no, why not? Because we already used it and repetition is not allowed. Can it be the 8? Can it be the 9? And I'm going to fill those in a second. I'm just going to go on and do the cases first. Okay, next one was starting with an 8. Can we start with an 8? What about the second digit? Doesn't matter. Anything there is going to be greater than 6,500. Can we start with a 9? Doesn't matter what follows. Okay, so all I did was just use logic to set up my cases, just went through the numbers one by one. I'm just going to repeat that. Can't start with a 2, because that won't be greater than 6,500. Can't start with a 3, can't start with a 5. The first one we can start with is a 6. Only choices here are the 5, 6, 8, because we can't repeat the 6. We can't use the 2 or 3 and be greater than 6,500. Second case, I can start with an 8, it's not going to matter. Third case, I can start with a 9, it's not going to matter. So let's go fill this in. This is 1 choice and 3 choices. We just now need to figure out how many are left. Well, how many numbers did we start with? We started with 6. We've used 1 in the first spot and 1 in the second spot. This is choices, but how many do we actually choose? 1. So if we had 6, we put 1 here and 1 here. We're left with 4. And let's just make a note of where that came from. 6 original numbers. Six original numbers. We used 2 of them in the first 2 spots. Well, why do we have this 3 here then if we only use 2? There's 3 choices, but how many do we actually choose? 1. What about the last digit? Why? Okay, so we had 6, we used 1, 2, 3, has to be 3 left. Total numbers of 6,500, 4 digits that start with a 6. Offer 46. 36 sounds better. Okay, case number 2, 1 for the 8. What did we put here? Why 5? Because you started with 6 and we have used. Then?
4 and 3. 60.
One choice for the 9. Following the 9.
5. 4.
What do we do with these 3 numbers? Why do we add them? Because it can start with a 6, or start with an 8, or start with a 9. So adding them up. You could, if you wanted to, combine these into one case. So if you wanted to, you could say that the first could be an 8 or a 9, which gives us 2 choices, followed by 5, 4, 3. You cannot combine with the 6. So you can combine the 8 and 9 case, but not the 6. Why does the 6 have to be its own case?
Because the second digit.
Because it has a restriction on the second digit. So you can do 3 separate cases, you can do 2 cases, but this has to be its own case either way. Does that make sense?
Yeah.
How are we doing? Good. B, turn and talk. Talk to someone. Like not, hey, how are you? Hanukkah's over. Okay, talk to me now. What do you want me to write down? Dead silence.
3 spaces.
I heard 3 spaces.
Correct.
The last one has to be 3 choices.
2, 6, and 8.
And somebody said 3.
Yes.
And then 5 and 4. Which is 6.
Why?
Because you have 5.
There's 5 numbers left.
Because there's 5 numbers left out of the 6. Why are you still up here? What is going on here? Go away. Goodbye. And why 4?
Because there's 4 numbers left after that.
And the total number of permutations? Who got it? Jenna, put the phone away. Okay, together as a group, you tell me, I'll write down. This is your ideas.
Would this be cases because it doesn't tell you how many digits?
Talk it out. I like your hair color.
They can't start with 4.
Well, it couldn't anyway because that's not our choice, but yes.
Oh, okay.
How many blanks?
Cases start with 1.
Ooh, somebody wants cases, okay.
How many digits? Is it? So 3 lines.
No.
Oh, I'm just kidding.
No, just a little slow, that's okay.
I can start with 3
I heard someone say 1.
and 300.
Okay, here's the offer. Talk it out.
It could be 2.
I just said talk it out, so anything you want to
The
change?
first one is 2 because it's either 3 or 2 because it has to be less than 400.
So can we combine a 3 and a 2? Okay. You could do those as separate cases if you want to. We're just going to combine them. Okay, so we agree this is 2. Why is this 5?
Because that's what we want to do.
Okay, so total for this case? Maddie, wake up. Okay, what's case 2 if we just combine 3 and 2 together? Yeah, does it have to be a 3-digit number? No, and this was an exam question I think 3 years ago, and most people scored 1 out of 3 because they thought it had to be 3-digit. Does it say anywhere in part C 3 digits? So the second case will be a 2-digit number. What's the third case going to be? The 1-digit number. Okay, so you really have to be careful to not read into the questions, but also to make sure you get everything that's there. Okie doke.
The first one can be 2 or 3, so there are 2 choices, and the second one is 5.
Okay, so 2 or 3 and 5, somebody offered?
No, 2 choices and 5 choices.
So 2 and 5, somebody offered? 4 and 5? 5 and 4? 6 and 5?
Oh, so it's 5 and 4.
I'm just writing it down. You're talking it out. Okay, why definitely 6 and 5? Right, because any 2-digit number is going to be less than 400. So it is 6 and 5, which gives us? Offer of 6. Agreement? Total? Why did we add them?
Because it can be either or.
So people who just gave 40, they got 1 out of 3 on this exam question. Made us very sad. Tell me how you feel on permutations. I like them, I kind of like them, I'm not liking them so much. That's not bad. I'll take a sideways thumb at this point.